Thank you very much, Marcus, for the introduction. And also thank you, as well as Michael, for this nice and comprehensive overview regarding UV light curing adhesives. Now I would like to come to the main topic of my talk, the rheology of UV curing adhesives. This presentation is divided into 3 different parts. First of all, I'd like to introduce you to the topic rheology in general, as well as rheometers in particular. Rheometers are powerful measuring devices and can be operated in various ways. Therefore, the second part of this presentation will focus on the basics of how to actually run measurements on UV light sensitive materials, but also about choosing the right measuring parameters for such experiments. Finally, we will connect all the dots by having a look at different UV curing adhesives we've investigated in our lab. The word rheology has its roots in the Greek language. It derives from the word rheos, which means flow, but also from the word logos, which means word or study. So basically, rheology is the science of flow, but also of deformation of matter. A rotational rheometer is used to measure flow properties under defined conditions, for example, defined temperature control. And an example for such a rheometer you can see in the middle of the slide. This is the MAS 4060 platform as an actual example for a high-end rheometer. Many people associate rheology with the determination of viscosity, but actually there's more to rheology than that. Many materials can be characterized regarding the flow behavior, and this is for many raw materials and final products crucial to get some information about specific application or processing behavior. As you can see on this slide, rheology is used almost everywhere. One big application, for example, is the food market, where rheometers are used to characterize flow behavior of chocolate or mayonnaise, for example. But also when characterizing polymers, paints, coatings, and so on, rheology is important and widely used in these markets. Rheology is also a great tool, of course, to obtain information about the flow or curing behavior of adhesives. Besides this, a rheometer can also be used to investigate, for example, occurring shrinkage during the actual curing process, but also the thermomechanical properties of the final cured product subsequently to a measurement. So really, really interesting measuring technique. The heart of each rheometer is its measuring head. The measuring head can be equipped with different types of measuring geometries and can be used to perform several types of measuring modes. For example, rotation or oscillatory measurements. When it comes to curing analysis, the rotation is not the preferred measuring mode. We will come to this later on. But when going into oscillatory measurement, which are the preferred ones, 2 different operation modes are possible. On the right-hand side of this slide, you can actually see a schematic of typical measuring geometry that is used for curing measurements, the so-called parallel plates geometry. And in between those 2 plates, there is a sample. So when we perform an oscillatory measurement, you can think of the basic movement like marking the front of both of the measuring geometries with a dot. And you can see when actually performing the measurement that this dot will move from one side to another side, indicating an oscillatory movement. So within a certain deformation range, the sample will be deflected during the measurement. Such an experiment can either be controlled by applying a certain force and measuring the resulting deformation. This is the so-called controlled stress mode, but also by applying a deformation and measuring the resulting torque, which is the so-called controlled deformation mode. Additionally, such a measuring head can also be used for the measurement and the control of axial normal forces throughout the entire measurement. Besides this, many rheometers are equipped with a high precision lift mechanism. That allows an accurate control of the gap between the upper and the lower measuring geometry throughout the entire measurement. This is crucial as many rheological parameters highly depend on an accurate, controlled measuring gap. The lift control also enables the adjustment of the measuring gap during the measurement to actually compensate occurring shrinkage or expansion. Additionally, the lift can also be used to move the upper measuring geometry, so you can apply or you remove samples before or after the measurement. As said before, a rheometer is a device that measures sample properties under defined conditions. One parameter that influences the flow behavior quite dramatically is the temperature. Therefore, there's a whole variety of different temperature controlled options available to meet the needs of different applications or measuring geometries. When performing UV curing experiments, the setup on the lower right-hand side can be used, for example. Here we implemented an optical path containing a mirror as well as a collimator unit directly into one of our temperature modules. From the back side, there is the possibility to apply a light source, for example, a UV LED. And doing so, the UV light can be guided directly from behind throughout the optical path to a glass plate and then to the actual sample. Using the collimator unit, homogeneous UV light intensity can be generated throughout the entire sample diameter. This way, the sample is illuminated in a defined and homogeneous way. As the cured samples stick quite well to the surface of the measuring geometries, we highly recommend to use disposable plates that can be disposed of after the measurement, which is also quite often used from our customers when performing UV light-induced curing experiments. If we plot the applied deformation of a sample between the upper and the lower measuring geometry in a rheometer as a function of time, we will see that both the deformation as well as the shear stress or the applied torque force that you actually apply on the sample will be showing a sinusoidal shape. In between both of them, there is a phase shift. And this phase shift is also called the phase angle delta, and is a measure for the sample's overall behavior. A shift of 0 degree corresponds to a purely elastic material, and this is occurring, both curves are overlapping each other, whereas a shift of 90 degrees corresponds to a highly or purely viscous material. Usually, most of the samples range between 0 and 90 degrees. Out of the deformation and the shear stress curve, many parameters can be calculated. On the right-hand side, you can see some of the rheological quantities. For example, the complex modulus can be obtained as a measure for the overall resistance of a material. But besides this, also the storage modulus as a means for the elastic part of a material, but also the loss modulus as the viscous part of the material can be obtained. This whole concept and the definitions of various rheological parameters might seem a little confusing right now, but this will all get clearer as soon as we are discussing actual measurement data. As already mentioned, oscillatory measurements can be performed by controlling the force and measuring the resulting deflection. When speaking in rheological terms, the force or the applied torque corresponds to the shear stress, whereas the deflection corresponds to the actual deformation of the sample. As soon as the curing starts, the material gets stiffer and stiffer, and therefore the deflection resulting from the applied force gets smaller and smaller. This leads to two actual drawbacks. First, the applied torque is always applied the same way. This means that the structure buildup during the curing might be disturbed or completely inhibited if the torque is set it too high. So the sample structure that is building up is simply destroyed throughout the measurement. Additionally, the angular deflection gets less and less and less until the lower resolution might be reached, and the measuring results are having a really high signal to noise ratio. To avoid this, we can actually do the exact opposite. We can control the deflection, deformation, and we can monitor the torque that is needed to maintain such a deflection. Here, the detected torque when actually measuring the uncured sample might be too low to ensure a good signal to noise ratio, but the structure buildup in general will not be disturbed throughout the experiment. Please note that the diameter of the measuring geometry plays a critical role here. The larger the diameter, the higher the detected torque at a certain deflection. This is beneficial at the beginning of the experiment when the sample is not fully cured and the rheometer is operating at very small torque values, but after the curing took place, the resulting torque might reach the upper torque measuring capabilities of the rheometer. Then the rheometer might not be able to actually deform the sample as it should be or is chosen by the operator. Then a smaller blade diameter will be needed to ensure a good signal to noise ratio again. In general, the ability for a gentle detection of a structure buildup during a curing is a big advantage of the CD mode. Therefore, it is the preferable mode for curing analysis. The last thing that has to be considered before pressing the start button of a rheological experiment is the applied frequency. Every oscillation is characterized by the length of its period. This means that the more time is needed for the system to perform an entire oscillation cycle, the longer it takes to obtain a single data point. A standard setting, which is used for many rheometer operators, might be 1 cycle per second, which corresponds to a frequency of 1 Hertz. When it comes to curing in general and UV light-induced curing in particular, the sample might undergo structural changes within seconds. Then a high sampling rate is needed to achieve a wide range of data points and to characterize even fast changes in the structure. Then it is recommended to choose a high frequency for this curing analysis. Now we have all the information that is needed to actually conduct measurements on adhesives. Here we have an example of a D-low photobond adhesive. Each sample behaves different within a rheological experiment. Therefore, it is mandatory to perform a controlled deformation experiment where you actually increase the deformation that is applied onto the sample. Doing so, you can actually define the deformation range in which the sample is not going to be destroyed throughout the course of the test or the subsequent test that can be characterized or can be used by using a rheometer. To obtain this range, we are using the so-called amplitude tree. In this case, we increase the deformation or the amplitude of the actual oscillation from 0.1 to about 100%. Doing so, we simultaneously recorded the storage modulus, G prime, which corresponds to the elastic properties, but also the loss modulus G double prime, which corresponds to the viscous properties of the sample. In this case, we see that the G prime is always lower throughout the entire measurement compared to the G double prime. This also indicates that the sample is very liquid-like, but this is also something that is not surprisingly, as we are investigating or talking about an uncured adhesive. Also, we can have a look at the delta, which is basically the ratio of G prime and G double prime. And what we see is that it's constantly about over 65 degrees. As we know from previous slides, the delta value can range between 0 to 90 degrees. So actually there is a threshold, a boundary at 45 degrees that is indicating a shift from solid-like to liquid-like behavior. In this case, we do not achieve solid-like, but liquid-like behavior, as the delta is always above 45 degrees. Such an amplitude sweep can be divided into three areas. First area is the area in which the deformation is independently from the rheological properties are independently from the applied deformation. This is also the region that we like to be within when performing actual oscillatory measurements. After this, there's a transition area which directly leads into a nonlinear regime. Here, the rheological properties are decreasing quite dramatically. As said before, when we want to perform rheological tests in oscillation, we always have to be sure that we are within the so-called LVR, the linear viscoelastic region. Please note that during a curing reaction, the sample structure is changing significantly. To be on the safe side, it is therefore recommended to perform an amplitude sweep both in the uncured as well as the cured region. Doing so, you can identify overlapping linear viscoelastic regions where you can be sure that the sample is always within this LVR regime. On the left-hand side of this slide, you can actually see a UV light-induced radical curing experiment. Radical curing means that as long as there is an irradiation of the sample and there is a reactive component available, the sample will actually cure. If the UV lamp is switched off during the experiment or the reactive component is gone, then the curing stops. Here we used an intensity of 50 milliwatt per square centimeter, and we illuminated the sample for about 20 seconds with a wavelength of 400 nanometers. Before switching on the LED, the viscous properties are dominating the elastic properties, so the photobond in this case behaves liquid-like. During the actual reaction, during the experiment, the structure changes and it comes to a crossover of G prime and G double prime. This crossover is also often referred to as the gel point and can be used as a parameter for a further evaluation. In this case, the reaction does not start immediately. The sample needs some time between the start of the irradiation and the onset of the actual curing. The so-called latency can also be referred to as some sort of a threshold that is present when using specific curing parameters. When doubling the intensity from 50 to 100 milliwatt per square centimeter, several interesting things are happening. First, the higher intensity leads to a faster reaction. So the transition from the viscous to the elastic dominant behavior gets faster and the crossover shifts to shorter time. Besides this, higher values for G prime and G double prime can be achieved doing the use of a higher intensity, which will also affect the mechanical properties of the cured sample. And lastly, the latency is significantly decreasing as the intensity is increased. So all these three findings are indicating that rheology can be used to characterize the structural changes of such samples quite well. Another important thing is the investigation of shrinkage, as it can have an impact on an adhesive joint. A great thing about rheometers is that this shrinkage can be detected simultaneously during the curing experiment. By controlling the occurring normal force, the rheometer automatically adjusts the gap height according to the shrinkage of the sample. So therefore, shrinkages, for example, of about 3% in the case of 50 milliwatt per square centimeters, or 5% in the case of 100 milliwatt per square centimeters can be obtained. Furthermore, when not only controlling the gap height, but measuring the occurring normal forces, one can also determine the shrinkage stresses that can be or that are occurring throughout the curing. For many applications, the thermomechanical properties of a sample are of great interest. When using an appropriate temperature control, those properties can be investigated subsequent to a curing experiment. Here we used another photobond sample and cured them at different dwell times using an intensity of about 200 milliwatt per square centimeter. Such dynamic mechanical thermal analysis tests can be done by increasing the sample temperature to evaluate, for example, the glass transition. The glass transition can be referred to as a temperature range in which the sample starts to soften. Many evaluation techniques can be used to characterize such softenings and to determine so-called glass transition temperatures. In this case, we use the maximum of G double prime, and what we see is that shorter dwell times are actually decreasing the maximum of the G double prime, which also corresponds to less network density and an impact on the mechanical properties. Lastly, I would like to discuss a mechanism in which the curing is triggered by using a rheolite, but the transition from a viscous-like to a solid-like behavior happens much slower compared to the previous samples. Here, the final structure buildup takes several hours until the adhesive joint achieves its final strength. In this case, this buildup happens at such a high extent that the geometry diameter to torque ratio gets unfavorable, and the signal to noise ratio is dramatically impacting the G double prime reading. When such things are occurring, smaller geometries can be used to improve the measurement performance and therefore the signal to noise ratio. Another interesting point is that the main network buildup occurs after the actual irradiation takes place. So-called dark curing mechanisms can be used to pre-activate adhesives directly after the application, but before joining the parts. Now, I would also like to take you by the hand and give a brief outlook what you can also do by using rheology. For an entire characterization of such a curing mechanism, it's also quite interesting to know what happens on a chemical level. Therefore, you can use, for example, this Rheometer module that we've developed that simultaneously can collect FTIR spectra while measuring the rheological measurement by performing the actual rheological measurement. As this presentation is now coming to an end, I would like to summarize everything that we discussed so far. First of all, rheology can be used to characterize different parameters like the crossover or the latency of UV light-induced curing mechanisms, but can also be used to investigate shrinkage or shrinkage stresses throughout an actual measurement. When adding subsequent measuring techniques like the DMA or the DMTA, also the thermomechanical properties can be investigated quite nicely. But also, if one likes to get an even deeper understanding about the mechanisms of the curing, also hyphenated method like hyphenating or combining rheology and FTIR spectroscopy can be used to get a deeper understanding of the sample. With that, I'm at the end of my presentation. I thank you very much for your attention, and I'm very curious about the questions that you might have now. Thank you.